So let's say I wanted to graph something simple, say r equals 3. So, I mean, I could go through all the work trying to convert that over to polar, but let's just think about it for a minute. What does it mean to be 3 units from the origin? That guy's 3 units away. That guy's 3. That's 3, that's 3. If we think about it, that's going to be a circle. Now remember, x squared plus y squared equals r squared. That's equivalent to saying x squared plus y squared equals r squared, 9. Anybody that's taken pre-calculus while you're taking this, you know that that's a circle centered at the origin of radius 3. That's why this is called r. When we write these r theta, we use the symbol r because it's a radius. R equals a number is a circle. On your graphing calculator, you have the ability to graph polar functions. So you could type this in and look at it. Here, I'll show you how to do it. So up here in y equals, clear everything out. I can go into oh, no, okay. I have to go into mode first. So go into mode and tell it right here under function that I'm graphing a polar. So right there, highlight polar, then go into y equals. And it's asking for r in terms of theta. So if I wanted to graph r equals 3, type it in, hit graph. I want to say zoom standard. I get that. Now, these graphing calculators that you guys spend like $100 on, they're terrible. I hate them. They're not worth $100. That circle that we just graphed sure as heck doesn't look like a circle to me, because your graphing calculator does not use the same length scale horizontally as it does vertically. Look how big that 1 is on the x-axis versus that 1 for the y-axis. So something as simple as a circle, your $100 calculator can't even graph properly. This should look circular, but it's stretched out horizontally. Hey, what if we wanted to graph theta equals a number? Say I wanted to graph, let's go with theta equals 30 degrees. So, I mean, I could go through the math. Tangent of theta is y over x. Tangent of 30 degrees is y over x. Tangent of 30 would be sine of 30 over cosine of 30. So 1/2 over root 3 over 2. So I think that's 1 over root 3. So that's y equals 1 over root 3x. That's a line. That's y equals mx plus b. It's a line that passes through the origin. So theta equals a number is a line. I wonder what that angle right there is. It's 30 degrees. So theta equals a number is a line. What if we wanted to graph something a little more interesting? But the next thing we might try to graph, if we were just making up functions on our own, is maybe we would graph r equals theta. So let's pull out our graphing calculator and look at that first, get an idea of what we're going to do. So I want r equals theta. Here's my theta in here. I hit graph. I'm going to zoom out so we can see a lot more of the graph. Is that 3? Now, your calculator only, because of our window here, only graphed a little piece of it, but you can see what we were getting here. So let's zoom in a little bit. It's a spiral. And this actually does keep going on, but our window only has us going from 0 to 2 pi. If we were to make an XY chart, or an R theta chart, so we pick our angles. We need to do these in radians. Then R equals theta, these are pretty boring. All the R's and the thetas are the same. This does need to be in radians. Oh, let me go back to the graph then and convert that to radians. Am I sharing? There, let me share. So in mode, let's graph this guy in radians. Let's go to my window. And let's say we're going to 8 pi. Let's go around 4 times. Hit graph and zoom. I don't know what R equals theta. Okay, let's ignore that. I don't know what happened to my graph there. Okay, I'll come back to that. Something funky happened.
Is it supposed to be in radian mode?
Yeah, I just put it in radian mode.
That's interesting.
My window. Oh, my step. I don't know why my step was so big. Okay, there it goes. Okay, so we get a spiral that's going around. So if we were to plot this point by point, so we do the angle first and then the distance. At an angle of 0, I go out a distance of 0. That's the point 0, 0. At an angle of 30 degrees, pi over 6. So I'm at this angle. I go out a distance of pi over 6, which is about a half. At an angle of 60 degrees, I go out twice the distance. So that distance, double that. At an angle of pi over 2, I go out pi over 2. So 3.14 divided by 2. I go out that distance and so forth. Over here, I'm rotating to my angle pi. I would go out a distance pi. And if we connect all those points up and we keep going, this is just going to keep getting bigger and bigger. It's a spiral. All right, last one. What if I wanted to graph R equals sine of theta? All right, let's make our chart here. So I'm going to pick my theta, that determines my R, and I'm going to plot a bunch of points in radians. Okay, so at 0, my R is going to be sine of 0 at 0. Sine of pi over 6, that's sine of 30 degrees, that's a half. Sine of pi over 3, that's root 3 over 2. Sine of pi over 2 is 1, that's sine of 90 degrees. Sine of, here we'll add in another one, 3 pi. Sine of pi, we're back to 0. Sine of 3 pi over 2 is -1, and sine of 2 pi is back to 0. Let's try graphing all these points. So that's the point 0, 0. At an angle of 30 degrees, I want to go out 1/2 of a unit. So I'm here at this angle, 30 degrees, I would go out 1/2. At an angle of 60 degrees, I'm up here at this angle, I would go √3/2. That's about 0.7. It's a little further away than that. So that's this distance. At an angle of 90 degrees, I would go out a unit 1. That would be maybe about right there. So rotate my angle, then walk that distance. Okay, now, maybe we'll add in an extra one here so we can see what's going on over here. Let's go, let's say that would be 3π/6, 4π/6, which is 2π/3. That would be this angle. Sine of 2π/3 is √3/2. So that would be, I rotate around to this angle, and I come out same distance I did there. That would be out here. What if I go an angle pi, 180 degrees? That says I'm supposed to go 0. I'm right back at the origin again. So I'm facing that way, facing backwards, but I didn't move anywhere. At 3π/2. So I start here, I rotate all the way around to 270 degrees. I'm facing that way, and I walk backwards 1 unit. That lands me back up here again. So I've already started recycling when I got back to 0. What we're getting is something that looks like this and goes around twice. From 0 to 2π, from here to here, I've gone around this circle twice. We can see that on our graphing calculator. Again, it won't look like a circle because our scales are wrong. These calculators are crap. But you can still get the idea. So I want to go back into y equals, and I want to graph sine of theta. Hit graph, and let me zoom in a little so you can see it. Now again, that looks like an ellipse, but it really should be a circle. That's just your calculator being done. So that's a circle. It's a circle of a radius 1/2. This total diameter is 1. So the radius is 1/2, and it's centered right here at the point 0, 1/2. So that point right there is the point 0, 1/2, and my radius is 1/2. I'm going to prove that to you by converting this formula here into Cartesian coordinates and then completing the square to write this in standard form. So I want to convert to Cartesian. This is going to be a question on your final, almost this exact same question. It's one of the most missed problems on the final, converting this thing over into Cartesian. So I have all my formulae. And I have these 4 formulae. I want to use these to convert this guy into x's and y's. So your first thought might be to use these. That's not helpful. That's not going to help. You want to use these formulas. Look at this guy. Y equals r sine of theta. Well, you look here and you go, I don't have an r sine. I only have a sine. I wish, I would be so happy if I had an extra r right there. Then I could just replace this with y. That would be helpful, but I don't have that. Similarly, if I did want to use this formula, I would be really happy if this said r squared, then I could just replace that with x squared plus y squared. That would be very helpful. So I wish there were a way I could get an extra r on both sides. Oh, there is. Multiply both sides by r. That becomes this. Oh, now r squared is x squared plus y squared. R sine theta is by definition y. Now we've converted to Cartesian coordinates. So that question right there, that will be on your final. You're done. That's where you would stop. I'm going to go just a little bit further with it just to prove to you that it is what I claimed here. It is a circle of radius 1/2. So if you've taken pre-calc, you know that your standard form for a circle looks like this. X minus x naught squared plus y minus y naught squared equals r squared, where the center of your circle is x naught, y naught. I'm going to make this look like that by completing the square. Need a little extra space here. I'm just going to get rid of that. So I'm going to get everything on one side. X squared plus y squared minus y equals 0. We take half of our middle number, which is 1, square it. So half of 1 is a half, squared is a fourth, and I add that to both sides. Then I group these together and I factor. That is a perfect square trinomial. That is y minus a half squared. Over here, 0 plus a fourth is a fourth. So this could be rewritten as x minus 0 squared plus y minus 1/2 squared equals 1/2 squared. That is a circle with center 0, 1/2 and radius 1/2. So what that means is r equals sine of theta is a circle, but it's not centered at the origin. It lives up on the y-axis. R equals cosine of theta would live here on the x-axis. So r equals cos of theta looks like a circle along the x-axis.